Hello everybody, I'm Stephen Foskett. I'm the organizer of Tech Field Day. The video you're about to watch is a recorded presentation of Intel's storage group presenting at Storage Field Day 11. The table is filled with invited delegates from around the world who focus on storage and storage-related technologies. They are bloggers and podcasters, and we've invited them here to participate in the discussion, to ask the questions that you would ask while you're watching. If you'd like to learn more about Storage Field Day or Tech Field Day generally, just go to techfieldday.com. If you enjoy this video, go to our YouTube channel, youtube.com/techfieldday, and you can subscribe and see literally thousands of other videos just like this one with all sorts of companies in storage, networking, wireless, and data center.
Okay, so we're going to talk about storage QoS today. And QoS in storage systems is something that folks have been trying for years. We're going to talk about self-managed storage. We're going to talk about autonomics. This is all kind of holy grail stuff, but I think we're actually getting a step closer each year. So I'm going to share with you some of the research that we've been doing at Intel Labs. I'm a principal engineer there. I've been doing storage 18 plus years at Intel, and SSDs have put so much wind in our sails with respect to trying to integrate those into systems. Things have gotten really exciting for us. So one of the things I want to talk about is cloud storage. So cloud storage is great. Layers of virtualization, disaggregated this and that, but these stacks are really, really deep. Right? There's a lot of latency, and so just simply taking SSDs and plugging them into the back end of a cloud storage system, a lot of times you don't see the performance, and it's a big waste, and that's a problem that we want to fix. So we've got some foundational technologies. One of them is called differentiated storage services. That was introduced in the previous talk. It's all about intelligently caching data, but it goes beyond that, so let's just go ahead and get into it. So von Neumann, he's kind of set up the problem that we have right here. This is all about feeding the beast, right? This is the basic computer architecture that we've had since the PC revolution, right? And so you've got, really smart things at the top of the stack. Is there a pointer on this? There it is, but it doesn't show up on that. Yeah. Very intelligent things at the top of the stack, CPUs, input devices, output devices, memory, and then at the bottom you've got the relatively unintelligent storage devices. And they're only unintelligent because you're not giving them a chance, right? If you look at the protocols that basically separate all these really capable storage systems from the CPUs that are running applications, you've got things like SAS and SATA and NVMe and Ethernet. For the purposes of interoperability, they strip away a lot of the context, most of the context that's living up in the stack. For example, what's going on in the operating system? Is an application blocking on this I/O? Are you updating the journal or are you reading a file? What's the quality of service for this class of data? Right? This is the kind of information, if we can get it through this semantic gap that's actually getting wider and wider over time, we can teach the storage systems how to optimize for specific classes of data. So that's kind of the challenge. With disk drives, it really wasn't a big deal, right? It's kind of, disk drives, it's, one size fits all. There's not much decision to be made when it goes to reading or writing a sector. But now, once you've got SSDs and you've got hybrid devices, you've got cloud storage, and you have all these resources that need to be provisioned for different applications, different VMs, different tenants, it better not be one size fits all. And if it is, someone's getting more performance than they paid for, or maybe you've just over-provisioned your system. So we want to get around that, right? So this widening semantic gap, think of the kind of stuff that would be really useful when it comes time to operating a storage system. And this is mostly common sense stuff, right? Groups, users, and access behavior, it'd be clearly nice to know that when it comes time to setting, say, a platinum, gold, or silver service level on an application. What about what the application is? Is it a database? Is it running in the cloud? Is it virtualized running in a VM? Knowing that stuff would influence how you treat the I/O in the back end. Let's go a little bit lower level, process, thread, and OS state. Just knowing that a write is synchronous, right? Most disk drives don't know that. They see a write and they just do it as fast as they can. Maybe it's buffered, maybe it isn't. Knowing that an application is blocking on that write would influence how it gets written in the back end. And then go even lower level, look at the file system. Knowing the difference between data and metadata, different file sizes, whether it's a transactional update or it's something else, would influence how you allocate storage in the back end. So what we want to do is try to take as much context as we can that already exists in the system and try to get it down to the block layer in a way that doesn't break interoperability. So that was the challenge that we had. So as you know today, the block API strips away all of this context for the purposes of interoperability. So it's a bit of a trade-off. How much information can we push down? Good question, though, is why are we still using blocks? right? I don't know. So I'm not going to fight it. I actually used to, I chaired the object storage working group in the SNIA, and we came up with a standard called OSD. I don't know if folks here remember that. You actually go to t10.org and you look at SAM3. There are a bunch of different storage devices. One of them is object-based storage device, which has a really rich object protocol that you can associate a lot of metadata with. It just never took off, right? You know, because blocks are so entrenched in our system that I don't see them going away anytime soon. So let's see what we can do with blocks. But first, a bit of history. Disk drive, 60 years old. Anyone remember the first drive? This thing here, the RAMAC, right? This is where our sector started, right? Big pizza-sized platters. I think the total capacity was about 5 megabytes, which was huge back then. That guy's main job was keeping these platters up and running, right? That's what he was the disk controller, right? This was before integrated device electronics, right? Then in the 60s, the media became removable. Okay, so now you can actually take platters and move them from one system to the next. So we're looking at media that can be moved, which is actually really useful. Then in the 70s, we had our first sealed drive. This was actually the beginning of the PC revolution. It was without this sealed drive, it'd be really difficult to put disk drives in our computers. And then finally, commodity drives in the 80s, and this is where the PC really got its start. Then we had the storage wars. Right? Remember the first PC you got and how big of a deal it was to have maybe megabytes in terms of capacity, right? Then we went from megabytes to gigabytes to terabytes. It's nice how I mean, this isn't exactly the way it was, but each decade was about like that, if you blur your eyes. And this is all with, you know, rotating media. It's with Rust. And most recently, we've got solid-state drives, right? But notice throughout this entire evolution, it's been read block, write block. That really simple protocol, and these drives are getting more and more capable, more and more intelligent. You can imagine CPUs making their way down to the disk drive. Maybe that disk drive isn't just a single device, but it's an array. But if you don't teach those CPUs about the data, there's not much they can do other than just the relatively boring storage stuff, right? And we want to get them past that. So if you look at cloud storage today, you know, her job, just like that guy's job 60 years earlier, is keeping a bunch of drives up and running, just rotating platters and solid-state drives. We want to teach cloud storage stacks about the applications that they're actually storing data for in a way that makes it much more scalable and performance improves quite a bit. So that's really the goal. So let's just talk a little bit about software-defined storage, because this is what this is our research platform in the labs. A number of different SDS layers out there, Ceph, Swift, OpenStack. You know, this is where the problem exists today and what we're targeting with this kind of performance optimization. So cloud storage, it is software-defined. If you look at it, you've got virtualized storage hardware for cost purposes, policy-based management, ideally, and it's massively scalable in multi-tenant. It's that multi-tenant problem where you run into problems because you've got a bunch of things that don't know anything about one another, different VMs, different applications, and you're trying to give them their own specific quality of service in the back end, and it's really difficult to do that if the back end doesn't know what those tenants are. Okay. But, you know, given the goals here, the way that it's implemented today, there's a lot of queuing and waiting. Someone who's ever stood up one of these cloud storage stacks and you measure round-trip latency, we're not talking nanoseconds and microseconds. We're talking hundreds of milliseconds. It's really painful, right? And 100 milliseconds, even if there's no one in line ahead of you, you're queued up behind 100 or 1,000 guys. Now you can actually count on your hands the number of seconds it takes to download an image in a system that's been oversubscribed. Right? And that's a big problem. You also have variable performance. And with variable performance, it's difficult to give service guarantees. It's those 99.999% outliers that really hurt you. And can we reduce those somehow? And also, failures are common. And the fact that things are always failing, a lot of times, well, it leads to the queuing and waiting, and it leads to more variable performance. So look at all the various cloud storage stacks out there. They implement software-defined storage in some form or fashion, and they all suffer from these same things, right? And we think that these foundational, what I'm going to call I/O hinting technologies that plumb the depths of the stack and give various layers information about the layers above and below can benefit all of these guys, okay? So let's just take Ceph as an example. This is how bad it could get. Are most folks reasonably familiar with Ceph, right? So Ceph is great. It's a great research platform. It's making its way out into the industry as product, but it also exhibits a lot of the challenges that we're trying to tackle here. So if you look at a guest app running in a guest operating system and all the various layers, and then you've got a cloud, which is really just the internet or Ethernet, and then you've got a backend storage node, and there are actually tens or hundreds of or thousands of these nodes. I'm just showing one. This is about the depth of the stack, right? Look at all the different layers that we cross. So we start off with POSIX files. So a guest application opens up a file, and it's reading or writing files through the POSIX interface. Then we get down into the guest FS, and it's issuing something like SCSI blocks. Now, these are virtual SCSI requests because it's a virtual SCSI HBA. It's running in a virtual machine. A lot of times, that virtual machine will take that SCSI request and turn it back around into a file protocol, especially if you're writing a virtual machine disk image. So maybe you've got a VM disk image that's living in the hypervisor. So SCSI requests are translated into file requests. And then you're back potentially down to generic block requests when you get down to an actual driver. Now, in this case, Ceph will take that and turn it around into Ceph objects. So now it's running a native object protocol over the Ceph fabric. So all the different layers there, and now we finally get to the storage node. The storage node gets a native Ceph object request, and what does it do? It takes that object and writes it into its local file system. So it goes back into POSIX again. Then the local file system gets the block request, or the file request, and turns it into a block request, and we finally get it down to the disk drive. Okay, so this is where I sit down here. If someone says, plug an SSD into that storage node and cache the most important data, I'll say, okay, fine. But give me some hint as to where the I/O is coming from and what its relative importance is. So what we need to do is start at the very top of the application stack and say, okay, if you want Platinum service, tag your I/O in some way that as it makes its way down the stack and it's finally presented to me, I know what the heck you're talking about, and I can differentiate one tenant from the next. And so that's really the goal. So again, the stack depth makes it really difficult to optimize down here at the low level. Multi-tenant requires differentiation, just not within one tenant, because not a tenant shouldn't have everything be stored on the SSD, right? Maybe only the journal goes on the SSD, and big files go on the backend HDD, right? But you also have to differentiate across tenants as well, again, like Platinum, Gold, and Silver. And at the end of the day, when you're talking about software-defined storage, whether it's an administrator making an informed decision or you've got a feedback loop that's automatically placing VMs in different storage systems, you want to predict whether performance goals are going to be met, right? And making that prediction, when this is a one-size-fits-all, your prediction is really wide and it's next to useless. But if you can have a predicted class service for various classes that the applications teach you about, then it gets us a step closer to what we all really need in the storage industry. Okay. So the SDS design goals, I kind of covered this, but let me go into a little more detail. You're basically virtualizing storage through a virtual storage controller. Some call it a storage hypervisor. And what's really nice about this is you have APIs for file, block, and object, and anything else that might come down the pike, like maybe even key value, right? That's a fourth one. Things are usually expressed in terms of logical volumes, and if we could assign QoS policies not only to volumes, but to things that live within those volumes, that's holy grail stuff for storage system administration. One of the reasons we want to do this is typically when you stand up a volume, since you can't differentiate easily today, you say, okay, this whole volume is going to be platinum, or this whole one's going to be gold or silver, and you end up over or under provisioning. And so in terms of acquisition cost, if you buy more storage or resources than you really need, that's something we want to get away from. So let's make the most efficient use of what we have. But if we can do all of this, there are all these benefits on the bottom here with respect to disaggregated storage and SDS controllers that we all know about, so I won't go into those details. But if you step up again from the perspective of a system administrator, this is really a generalized assignment problem. If you Google for the file assignment problem, you'll actually, IBM came up with it first back in the 60s. We've been trying to do this for decades, and it's still here today. So if you've got a bunch of different applications, I'm showing different application servers, basic questions like where should I store OLTP data, right? Can I co-locate my web storage and my application storage? These are fundamental questions that really smart, seasoned administrators try to grapple with today. They've got heuristics, they've got rules of thumb. They're overworked, underpaid, that sort of thing. So if we can develop some system software that will help them make more informed decisions, that's kind of the goal. And again, the fundamental premise here is that for them to do that, you have to provide this hinting information, and I'll provide a lot more detail there. But if we can do that, then this mapping problem from applications to storage systems, there's not as much black magic anymore. You'll know for, say, an iSCSI storage system what service levels that is capable of supporting and which applications are actually requesting it, right? And we do the mapping in an intelligent way. So the biggest challenge is, now let's go into the kind of the automation realm. Imagine that all of the stuff I'm talking about becomes standard someday within an automated feedback loop. We need to monitor workloads. That's the foundational thing. If you don't know what workloads are doing, what they need, what they're expecting, the rest of the stuff is impossible, in my opinion. Then once you've monitored workloads at the appropriate level of granularity, using hinting, for example, to tell you what workloads are actually doing, you want to model storage systems, right? You want to predict performance. And the reason you want to make this prediction is because taking a workload offline, migrating it to a new storage system just to see how fast it goes, we don't have time for that. So you're bringing a new storage system online, you've got new VMs coming online, and you want to know quickly, where should I place this VM? And will its SLAs be satisfied, right? Administrators make these predictions real time today. Google SREs, they wear pagers so when things go wrong, but not everyone's a Google, right? Not everyone has that kind of staff in a data center. So not only do we want to automate for the big guys, but for the folks that can't have all the staff running around, what can we have in system software that helps them get through this, right?
Yeah, you can't have policy-driven management without modeling.
That's exactly right.
Yeah.
Yeah, good point. So yeah, so modeling it's really fundamental here. Right. If we can, and this has been a challenge for decades. I mean, you go get a PhD in storage systems, and 4 out of 5 guys are trying to build a model, right? Okay, and all these different ways of building models, decision trees, neural networks, statistical models. It's a lot of fun, but there are so many moving parts. And the goal, just a little digression here, the goal isn't to come up with the optimal solution. A lot of times as a student, you want the optimal, and that's the bar. The bar is really what folks do today. And if you can do as good a job as they do, or maybe even a little bit better, maybe even a little bit worse, but they get to do better things, then that's a win. So that's kind of where we're setting the bar. So, and that takes us into the optimization component. So assigning workloads to storage, it's a big game of Tetris. It's a bin packing exercise, right? And this optimization model here calls the storage models over and over again with these what-if scenarios. What if I were to put these two workloads together? What if I were to set this caching policy in the SSD cache? Is it going to meet my 99th percentile latency guarantee? And then once we've figured it all out and we need to orchestrate something, then the system has to be agile enough that we can say, okay, this is the right policy for a virtual machine in terms of storage caching, or this is the right storage system for you to place that virtual machine disk image on. And then something like OpenStack Heat, where it has a list of things that a VM needs, that's where the orchestration happens, all right? So let's put it all together in a pretty picture here. At monitoring, you monitor everything that's important for establishing specific SLAs and meeting those, right? I'm showing performance, reliability, availability, power, and it could be some interesting combination of those. Then once you've monitored the system, you want to optimize the assignment of resources. And this is basically where we map virtual machines which have logical volumes to the storage systems. And one part of that is setting caching policies in the storage system on a VM by VM or an app by app basis. But for this optimization step to work, we consult these models over and over again to make our prediction until we're basically doing a hill climbing search, find the peak of, lowest latency or highest throughput or highest bandwidth or lowest power or highest reliability, right? So we optimize whatever objective function is. And then once we've figured it out, we go to our orchestration component and we bring things online. And then we stand back, right? And we monitor the system. And if the SLAs are being met, then life's good. If things break or applications legitimately change what they're doing or what they need, then we go around this loop again. So this is the holy grail vision that storage researchers have been going after for decades, this basic picture right here. If you look at, SOSP, Sigmetrics conferences, and folks talk about automated administration, you'll see something that kind of looks like this. But again, each decade, it feels like we're getting a little bit closer to cracking this nut, and it's just about setting the appropriate bar. Okay? So this is one of the foundational technologies that we believe makes this feasible, right? And we got into this game when folks said, take SSDs, plug them into an existing disk storage system, and do something intelligent with it. And what we found out is that we really needed more information plumbed in the stack to make that happen. And once that's there, a lot of this other automation, it starts to look a little bit easier, okay? So this is what we call DSS. It's an I/O classification technology. Has anyone been tracking the NVMe and T10 work on I/O hinting in general, like stream IDs? Right? Like, very quickly, a stream ID tells you very simply sequential streams as they're being written into an SSD. So if you have 16 VMs writing 16 things sequentially with 16 identical lifetimes, like if you delete one stream, that entire stream will be deleted. Just knowing that when it comes time to flash management takes you a really long way. Otherwise, garbage collection becomes really difficult. So the NVMe guys recognize, I want to differentiate one stream from the next. Similarly, the SCSI guys, and I've been working with T10 on this, had the other reasons that I mentioned. But in general, I/O hinting is something, people have been talking about it for decades. Now we have some real use cases that if it's not there, you take a big performance hit, and in some cases, a big reliability or power hit. So let's talk about bridging the semantic gap, all right? This is really all about the I/O hinting. So with each I/O request, we don't want to change the read block, write block protocol, but it turns out there are enough free bits in these read and write commands that we can pack in a little extra information. Think of it as a label, like we've got a labeling gun, which allows for configurable storage policies on a class-by-class basis. So whether we're talking about performance, reliability, or security, now at the block level, not everything is going to be one size fits all. We're a step forward. And the best part about this is it's completely backward compatible. Someone that doesn't know about hints, someone that doesn't want to know anything about hints, they can just ignore the field, right? And then you get the performance that you normally would. Unfortunately, it's kind of one size fits all, but it doesn't break anything. And there's not really a correctness issue here, especially with performance, because we're not changing what blocks get read and written in the storage system. We're just telling the storage system what's inside each of those blocks effectively and what the expectations are with respect to performance, reliability, security, and those kind of things. So let's go to a fun analogy. Labeling stuff, it's common sense, right? If you're going to package up stuff in your house to move, and you're going to contract a moving company, which is the storage company in this analogy, clearly you have to label what's in each box. Think of these boxes as sectors, right? Label what's in the box. Once it's labeled, which is basically a one-time thing, you know, kitchen stuff is always going to be kitchen stuff. The file system journal is always going to be the file system journal, right? Database transaction log, it's always the transaction log. So you do the labeling up front, you pay that cost once. And then, depending on the capabilities of the storage system, you assign policies to all the different classes of data. For example, kitchen stuff is fragile and this side up. The journal is fast access for writes. You know, so think about the different policies you can have in a storage system. So applying the analogy, you know, the classifiers, it's the same that we do in differentiated storage services. They're hints to the storage system. It's on a class-by-class basis. Then once you've done that, you assign storage policies to different classes of I/O. Someday, those policies might be standard, right? So you can imagine that NetApp and EMC and IBM and even your cloud service providers, they provide standard policies like next day air, DHL and FedEx, the UPS, they all have them. But they also have very specific service level agreements that provide value add for them. So it's going to be very similar. And then it's up to the storage system to enforce these policies. The applications don't care how they're enforced. They don't care what mechanisms are in the back end. If they specify that they need a specific amount of latency, they don't care how that latency is satisfied as long as it is, right? And that's what the storage vendors really need to differentiate, okay? Any questions on kind of the high level?
It's a really good analogy.
Yeah,
that's a really good slide to illustrate the concept.
Thank you. And you know, a lot of folks when they see this that aren't in the storage industry, they're like, "Hasn't it always been like that?" I'm like, "Sadly, no." You know, you look at, yeah, exactly. How do you guys get by? Yeah, you look at a disk sector, and it's like, "Oh, there's something in there, but I don't know what it is." Right. So let's go ahead and move on with the analogy and see this is what the architecture looks like. So on the right side, I'm showing a storage system. This could be a single hybrid drive or a big JBOD or a big, you know, cloud storage server. What's the only thing that matters there is that a decision needs to be made. You have different QoS policies, you have media, and it's not one size fits all. But without information from the left, you don't know how to direct I/O to the various pools of storage. Imagine that storage pool A is all SSD, storage pool B is HDD, and storage pool C, just for fun, let's call it tape, right? On the left here, we've got different stacks, different layers, right? All the green boxes here, this is where we're differentiating. This is where we're doing our research. So every layer can tell you something about I/O that it's either creating or it's passing on further down the stack, right? So here are some examples. Look in the middle. We basically establish this table and we communicate it to the storage system before the storage system comes online, so it knows what's expected of it. This is basically your contract with storage. Maybe we have metadata, boot files, small files, and media files. You know, obvious classes of data that clearly want different service levels when it comes time to storing data. Now, as an example in terms of the performance levels you could get, low latency, high bandwidth, and high throughput, maybe 3 distinct levels of service you could get from your storage system. Right. So before you bring the app online, you just fill out this table, you communicate it to the storage system, so now it knows what's expected of it for each I/O. Now the only missing piece is how, with each I/O, do you communicate what the class is? Okay, and this is where SCSI comes into play. It turns out there's this thing called the group number in the SCSI CDB that's 5 bits. Actually, I think it may have grown to 6 bits. It's not being used by anyone. Right? I think IBM used it for accounting purposes, so you can tell who's reading and writing what. We said, but it's reserved. We said, okay, T10, can we use that group number, the 5 bits, to specify 2 to the 5th or 32 different classes of data? And they're like, sure, that sounds reasonable. So what are the classes going to be? You know, the standards guys, they want to say, okay, journal, file system, metadata, so on and so forth. They said, no, we just want an opaque classifier that's vendor specific to start off with. And T10 just needs to have the appropriate plumbing so that we can get it from the host operating system to the storage system, right? We can do very similar things with NVMe, right? And that's where the whole hinting discussion is. So it turns out there is room in the command set. We're not changing what's being read or written, no correctness issue there. We're just labeling the I/O so that the back end knows what to do with it, okay?
I think the most surprising part here is that there was room to do that without changing the protocol.
Yeah, well, if you look at most of the command specs, they future-proofed it a little bit, and also with respect to staying aligned on cache lines and sectors and pages. Sometimes they pad things out and they don't know what to do with it, so they say, okay, this is just reserved, and we totally benefited from that, right? Nice. So there's a close-up of the group number, and if you look at t10.org and you look at the latest disk command set, it's SBC4, you'll see this reference there with some examples of the kind of hint that you can put into that field. And for those that are familiar with SCSI mode pages, it gives you really an unlimited number of policies in the back end. So this group number, this hint, this classifier, this tag, this label, it's just an index into a table of an unlimited number of things that you might do with this I/O. So you can imagine every initiator can classify its I/O in a way that's specific to the initiator. And each class is an index into a table which is stored as mode pages. So it gives you about as much flexibility as you need to have various forms of QoS for each initiator. But buyer beware, the labeling gun problem. Remember these? You get a labeling gun and you start going crazy, labeling everything. You don't know when to stop, right? If we unleash this on the industry and say, okay, just label all your stuff, and then now storage systems are just bombarded, they'll have a big data problem, which actually could be kind of fun, but it could be a mess. So what we're doing is we're saying, okay, let's make sure that we standardize the plumbing in such a way that folks don't get confused, and let's start with system software. Let's start with file systems, database, cloud storage stacks, hypervisors, guys that already have enough information and they're already policing their tenants in such a way that they know how to divvy up resources. This is a tool for them. And then once that's figured out, then maybe the applications can take this labeling gun and make specific requests of the I/O that they're generating. So that's the kind of the evolution that we see here.
How do you see that standardization taking place?
Ideally, the plumbing will be standardized first, and all the hints will be completely opaque. But we'll have enough room that you can pass down just about as many hints as you need to. And then standard hints will evolve. And like the NVMe guys are already looking at this. They're looking at data lifetime and temperature. And the SCSI guys are looking at things like frequency and recency of access. So hints that everyone kind of agrees that that's a good thing, we'll start standardizing those, and everything else is vendor specific. And I think the vendor specific is important because it lets storage vendors really differentiate. Just like UPS and DHL, they say, we've got better quality of service, so come to us, as opposed to everyone just doing the same thing. Right, so there's going to be some stuff that's standard, some vendor specific. As the vendor specific stuff gets boring and everyone does it, then it becomes standard, and there's always going to be vendor specific innovation.
It'll be interesting, to say the least, between the software companies that want to provide the policy-based management and the storage companies that want to basically still maintain lock-in.
Oh, and there's always that tussle, so this is...
Well, software is becoming more powerful, though. Now,
yeah.
Right? I mean, we're entering a new a new age. You know, you've got vSAN technology, you've got things like Ceph, you've got, there are different players in the software world that are a lot more powerful than they ever were before.
Yeah.
You know,
Agreed. Yeah, so it is going to get interesting. And just to go back a little bit to the object storage story, this was almost a technology that compromised a little bit. If object storage were to go native to a disk drive, you wouldn't need to do this stuff necessarily, because every object on the disk drive would have all this really rich metadata. But that never took off because object storage just shook up the storage industry a little too much. File system developers, guys that lived in the host OS, database developers, folks that really liked building B trees and doing block allocation, object storage was saying, you don't need to do that anymore. The B tree is now going to live in the disk drive. Now, if you were a file system developer, you probably wouldn't like that too much, unless you maybe change your entire development platform to now you're an embedded system within a drive. So for business reasons, this is my own personal opinion, native object storage never really took off. But then the cloud came along, and big object storage, like in the form of Hadoop, took off. It's just a larger level of granularity, but you still have blocks inside each of these devices. So the way to optimize those blocks is to basically use this technology. Yep. So let's dive a little bit deeper and look at some of the specific prototypes. You know, we've been working on this a number of years at Intel, and we're looking at the various stacks, and we're saying, okay, what hinting plumbing is needed, and what kind of hints might we have? And then what would we do with those hints in the back end? So let's look at ext3, ext4. Anyone familiar with Lustre? Yeah, Lustre's internal Idiskfs. Basically, it's a variant of ext4. And then for fun, NTFS, you can do this in Windows too, right? So we said, okay, what are some classes that kind of apply to each of these file systems? So we started off with file system metadata. Block bitmaps, inodes, B trees, superblocks, group descriptors, all that stuff. We want that to be high priority. So we said, okay, that's cache priority 0. 0 is the highest here. Then we've got the file system journal, and we've got directory entries. And then what about file sizes? A disk drive doesn't know what a file is, definitely doesn't know what a file size is. So let's teach the disk drive about the size of a file. One reason that's useful is knowing the size of a file lets a hybrid drive with a little bit of cache make and enforce a really obvious caching decision, like cache all files smaller than a megabyte, right? So one of the things that we wanted to do with our SSDs is just have simple, obvious policies like that. And so this is the first set of policies we came up with. So to get that information, all we had to do was modify the Linux file system, right? So we went into ext3, and just by virtue of where you are in the code, like if you're in the B tree or inode code, you know that you're reading or writing a B tree or an inode, right? And you can go in there and say, okay, let's just use this classification gun, this labeling gun, to specify it as such, right? So we modified the kernel so that every IO command has one extra field that tells you what that data is. And the kernel doesn't need to know anything about the field, it's just a number. So again, like in the inode example, we go in, and when you're reading an inode, we assign inode, let's say group number 3. Right, so you read or write the inode and you specify group number 3, and then now that's passed all the way down the stack. And that group number 3 is what's used to look up the policy for an inode in the back end, which is that storage system over there. So that's the local file system. Now, before we even get to caching, for the purposes of storage optimization, like block tracing, just tracing things at the disk level, look at what you can do now. So I'm showing a block trace, and so Linux block trace and block parse traces every IO command. The block that you're reading or writing, the number of blocks from that offset, and whether you're reading or writing it. It also gives useful information like process, group, and user ID, and that kind of thing, but it doesn't make its way down to the storage system. What we've added to that is the group number, and I've already gone and translated the group number to the class of data. So if we were to echo hello world to the file foo that already exists, and then we sync the file system, what you can see here is the read, modify, write. You see that we're reading out the 4 kilobyte page because we're not writing a full page, and file systems only write in full pages, right? Even if you can write at the sector granularity on a disk, you mount a file system with 4K pages, you'll never see anything less than 4 kilobytes being transferred, right? So we see the 4 kilobytes being read from disk, then we see the new hello world with the 13 bytes up being written to disk, right? Then all the metadata updates. We've got 4 journal updates. When we sync the file system, the journal's cleaned, and then everything's written into the inode. Right? So just for the purposes of debugging a file system and making sure that the right things are happening, and then eventually with an eye on optimizing the file system, you can see how that classification information is already really useful. Right? Most storage developers today, unless they're also looking at database code and trying to or file system code and trying to correlate what's going on in the OS or app layer with the storage layer, they don't see this correlation here. And so it makes it really difficult to optimize on an IO by IO basis. So in this example, we see that 7 IOs, totaling 28 kilobytes, were needed to write the 13 bytes of data. 13 bytes of data being hello world. Right. So take that example, choose your favorite application that has an IO bottleneck, and imagine tracing it like this and being able to differentiate what the IOs are actually doing. Right. So it's really a fundamental building block and a tool in Intel Labs, because someone says, oh, my application is not running fast enough. You're like, okay, are you running the DSS kernel? Great, go ahead and trace the IO, and we'll give you a breakdown on what's what, and then we can start root causing from there. Okay. So let's go to a database. This is totally different. So were the file system optimized for file system metadata structures and big files versus small files, a database might have everything within one big file or one big volume. And so the file system classification scheme obviously doesn't make sense for a database. So we had a database guy come in. Now this is an intern that came in for the summer. He knew about databases, he knew about our stuff, and he was able to accomplish this in a couple of months. Just shows you how easily this can be done. He said, okay, well, there's some obvious database classes, the system tables, temporary tables when written, temporary tables when read, sequential tables, index files. And I'll tell you that the first 4 should be cached and the second 2 shouldn't, because it's just a waste of cache space. So we said, okay, go ahead and modify PostgreSQL to add this labeling gun information and then bring up the database, and we'll enforce your policies in the back end. So he didn't have to build the storage system. The storage system was already built. He just came in and modified the database with the labeling gun, specified the policies, and then we did our thing, right? And so the neatest anecdote from this is when he came up with temporary tables on write versus temporary tables on read. Because what we found with existing LRU temperature recency-based algorithms that try to get all the hot data into the cache, when you write a temporary file, before you come around and read it again, it's been long evicted. And when you go back to read it again, you're doing all these capacity misses from your cache, and you're pulling it into the cache now, and it's a cache miss, and you don't access it again. So you're just doing all this unnecessary work. So he said, okay, I've got a really simple policy. When something is labeled as a temporary table, it gets pinned in the cache until it's read, and then once it's read, it's immediately evicted, right? So it's kind of the obvious thing that the database guys want to do, but since they don't have control over the right side, they can't do that, and they hope for the best. Well, this contract that we've established basically gives them control, but not control over the mechanisms, just control over the policies that they want, right? So that, yeah.
That's a question. So, so far everything you've been talking about has been cache priority. There's also ultimate write priority. Is that something you're...
It's on our roadmap.
Or
yeah, not in these.
Right now you're talking about caching.
This is it's focused on caching, but you're absolutely right. I mean, once you've got these labels, you can do a bunch of other stuff, and it is on our research roadmap.
Okay.
Yep. So that was the database. Now this one was interesting because we're now outside of the kernel, right? So how do you get a hint from application space into the kernel, right? And we wanted that 5 minutes. Wow. We wanted that hint to travel with each IO command, meaning in band. So what we did is, okay, we've got to get it through POSIX, so let's go ahead and come up with a new file flag. Now, I'm not suggesting that this is the way the Linux kernel guy's doing it, as long as they find a way to get our hint with the IO whenever, then we're fine. But we said, okay, when you open up a file and you want a hint on it, you specify oclassify. That oclassify file is a hint to the virtual file system that says every IO that comes down, there's going to be one additional scatter-gather element that's not real data, it's just a hint. So you know to extract that pointer, that hint, and it points you to 1 byte, which is that opaque classifier that gets copied into the CDB. So in this example, what we've done is we went ahead and we wrote hello world again from the database perspective, which is 13 bytes, and we attach to that 1 byte of hinting information, and then we issue the 1 write command into the OS. So the obvious benefit here is that the hint travels with the IO request, as opposed to something like fadvise. I don't know if folks are familiar with fadvise, where you can fadvise block regions of a file, but it's out of band, and now you've got a synchronization problem. So ideally, when the IO is presented, you know what it's for, rather than hinting on it out of the side. Okay. Now, I won't go into detail here, but everything that I've just described can be run recursively within a virtual machine, within a hypervisor. So all those file system classes, all those database classes, imagine that's running in a guest OS, and all of that stuff gets funneled down into 1 logical volume, or 1 virtual machine disk image. So you basically need to copy these hints down and not lose anything. It's, it's like leaving breadcrumbs as you go. Now, just to give you a sense for how complex that can get, getting hints through QEMU. This is Linux, the Linux virtual machine. You have to go from the guest app to the guest OS to the guest FS to the guest block layer. Then the virtual SCSI request to the HB to the VMM to the disk file. These are all those different layers I was talking about. Finally to the file system and storage system. And that's actually simplified because the file system storage system could do all the stuff on the top all over again. So it's turtles all the way down, right? So what we've done in Intel Labs is added the necessary plumbing, and it's not that much. It's just a lot of different parts of the stack you have to touch to make sure that those hints are translated and copied from one layer to the next. And again, QEMU in this case is just a user process. So that OClassify flag that we came up with for passing hints into the Linux kernel, QEMU in this case is a user process that's passing hints into the Linux kernel. So again, it's all very recursive. I don't think I'll cover that. But if you do this with Ceph, for example, so imagine everything that I just described is now implemented, then you've got a bunch of different Ceph tenants. Some of them are virtualized, some of them aren't. As they're going through the native Ceph protocol, we can now differentiate all the different classes of data that are being transported over native Ceph objects. For example, we've got user class M, whatever that is. We see some file system metadata, and we see a file that's less than 4 megabytes in size, right? Then on the other side, for each Ceph tenant, you can go and assign policies to all these different classes. And that's kind of this holy grail vision that we're going after. So in terms of the research roadmap, Gen 1 is block level hinting. This is at the SCSI or NVMe layer. Gen 2, we go from the kernel into user space, and we start having applications tell us about what hints they need. And then Gen 3 is object level hinting, where you're sending hints over something that looks a lot like a REST API. And so we're planning on releasing open source through the storage builders community. I've got 1 more minute. And so look forward to more here, and we're all about collaborating. So we don't get real customer workloads unless we work with customers. So that's kind of that's the open door. This I talked about. Next time, we'll go into more detail here, but once we've got all that hinting information, we can use it to do a bunch of really cool stuff. Let's just do a quick foil flip here. And you can imagine that this is maybe next time. Where's the this one? Things get really interesting with machine learning, right? And it's actually, machine learning is all about using feature vectors to predict things. Well, these hints are very useful feature vectors. It gives us something to actually build a regression model around, or a decision tree around, or a neural network around. So we think that this will just lead to other opportunities. So.